Hello everyone, I am Gracelyn Brianas of BECE 2B. For today, we are about to explore these topics with my groupmates. I was assigned to report the first topic on the list, and now let's go. Getting to know UARM. So, what UARM is? UARM is the acronym for Uniformly Accelerated Rectilinear Motion. It is the motion of a moving object in a straight line with a constant acceleration. Since the acceleration is constant, the change in speed remains the same every second. So here, to get to know UARM better, here are three properties UARM possess. First is the trajectory is a straight line, and therefore the normal or centripetal acceleration is zero. The instantaneous velocity changes its magnitude or speed uniformly, and that it increases or decreases by the same amount in each unit of time. This implies the following point. The tangential acceleration is constant, therefore, average acceleration is the same as instantaneous acceleration for any period studied. So a body moves with constant acceleration motion or uniformly accelerated rectilinear motion, or the UARM, when its trajectory is a straight line and its acceleration is constant and that different from zero. This implies that the velocity is increases or decreases its magnitude uniformly. So, we have here an example. In our example, the car describes a UARM since it moves in a straight line with constant acceleration equivalent to 2 meters per second squared. Notice that in each second, the velocity and the distance traveled by the body increase based on the value of the acceleration, based on the value of the acceleration in the previous second. Also, notice that although colloquially we make distinction between an accelerating and a braking body from the point of view of physics, both are uniformly accelerated rectilinear motion. The difference is that while one has positive acceleration, the other one has negative acceleration. So, let's proceed. So, we have here the equations. V equals to V sub O plus A times T. Next, here is X equals to X sub O plus X sub O times T plus 1/2 of the products of A and T squared. Then lastly, A equals to CTE, where X and X sub O is the position of the body at a given time X and at the initial time X sub O. Its unit in international system is the meter. And we have here the V and the V sub O are the velocity of the body at a given time V, and that initial time V sub O. Its unit in the international system is meter per second squared. And then A, which stands for the acceleration of the body, and it remains constant with a value different from zero. Its unit in the international system is meter per second squared. And lastly, T as the time being studied. Its unit in the international system is the second. So, I have here a sample problem. It says, a cyclist starts his morning ride after 10 seconds his velocity is 7.2 km per hour. Take note. And at that moment, he sees a dog approaching and slows down for 6 seconds until the bicycle stops. So calculate the following. First, the acceleration until he begins to slow down, the braking acceleration of the bike, and lastly, the total distance traveled. And then, to solve the question A, let us first identify the given data. So we have here v sub o equals to 0, which is the initial velocity, and v is equals to 7.2 kilometers per hour, wherein the velocity at 10 seconds. So here, the movement can be broken down into phases. A first phase in which the acceleration is positive, wherein a is greater than 0, and the second where the acceleration is negative since he is braking, so it is a less than 0. So transforming the velocity to SI units, we have that velocity at 10 seconds is v equals to v equals to 7.2 kilometers per hour times 1,000 meter per kilometer times 1 hour over 3,600, that resulted to 2 meters per second as our initial velocity. And so we are asked for the acceleration in the first phase of the motion. Since we have the initial velocity, which is 0 meter per second, the final velocity, which is the 2 meter per second, and the time between them is 10 seconds. We can use the velocity equation and calculate the acceleration directly. So using the formula v equals to v sub o plus a times t, that leads us to directly use the a equals to v minus v sub o all over t, and then substitute everything, and that we have here a equals to 0.2 meter per second squared. And then we have the question B. First, we have to identify the given data. So we have here the initial velocity would be the final velocity of the first phase, which is initial velocity initial velocity 2 meters per second, velocity at 6. And since he stopped at that moment, the velocity will be 0. Applying the same equation as in question A, we put the formula and then substitute everything, and that gives us negative 0.33 meter per second square, since we are asked for the acceleration in the second phase. And then, so to get the second phase, we have the formula inputted, substitute everything, and that leads us to x equals to 10 meters. And then for the second phase, same process, using the formula and then substitute everything, and that gives us x equals to 12 meters. And lastly, add the first and second phase to get the total distance traveled. So we have the final answer, 16.06 meter. And here I end everything. So let's proceed to the next reporter.
So now, let us proceed to the next topic, which is about the position vector, velocity, and acceleration. So what is a position vector? A position vector is a straight line having one end fixed to a body and the other end attached to a moving point, and used to describe the position of the point relative to the body. As the point moves, the position vector will change in length or in direction, or in both length and direction. Position vector is also defined as a vector that indicates either the position or the location of any given point with respect to any arbitrary reference point like the origin. The direction of the position vector always points from the origin of that vector towards the given point. So how to find the position vector? Before determining the position vector of a point, we first need to determine the coordinates of that point. Let's suppose we have 2 points M and N, where the coordinates of M is x1 and y1, and the coordinates of N is x2 and y2. Next, we want to find the position vector from point M to point N, or the vector Mn. So to determine this position vector, we're going to subtract the corresponding components of M from N. So position vector Mn is equals to x2 plus y2 minus x1 plus y1. Notice that this x2 plus y2 is the coordinates of the N, and this x1 and y1 is the coordinates of M. So if we're finding the position vector from point M to N, so we're going to subtract the coordinates or the components of point M from point N. And so if we're finding the position vector from point N to point M, so we must subtract the corresponding components of M from N. So dire, the position vector Nm is equals to x1 plus y1 minus x2 plus y2. So if ato pong balihon, if arita magsukad ni N niya to M, so we're going to subtract the coordinates or the components of N from M. So now let us have an example. Given 2 points A and B, where the coordinates of A is -4 and 6 and the coordinates of B is 5 and 12. Determine the position vector AB, then compute the magnitude of the vector AB. Solve it in terms of I and J. So remember that we're told to solve the position vector from A to B. So we're going to subtract the position vector or the coordinates of A from B. So in here, position vector AB is equals to x2 plus y2 minus x1 plus y1, where x1 and y1 represents the coordinates of point A and x2 and y2 represents the point B coordinates. So here, the position vector AB is equals to 5i plus 12j minus -4i plus 6j. So atong i-subtract ang components or coordinates sa coordinates sa A ngari sa coordinates sa B. So mo ni siya na nahimong 5i plus 12j minus -4i plus 6j. And remember, we are having negative sign here, so we're going to distribute it to -4 and 6. So negative times negative is positive, and then negative times positive is equals to negative. So here, in here, position vector AB is equals to 5i plus 12j plus 4i minus 6j. And upon evaluating, 5i plus 4i is equals to 9i, and 12j minus 6j is equals to 6j. So, mo na niya ang atong answer, which is the position vector AB is equals to 9i plus 6j. And then, we're told to get or to solve for its magnitude. So thus, the position vector AB is equivalent to a vector that starts at the origin and is directed to a point 9 units to the right along the x-axis and 6 units upward along the y-axis. So this I represents that this is in x-axis, or it is horizontal, and J represents that this is in y-axis or vertical. So when we say positive 9, this is going to the right because going to the right, or the x-axis, the positive x-axis is going to the right, and here positive 6, so it is going upward because the positive y-axis is going upward. So that's why it is 9 units to the right and then 6 units upward. So now let's let's determine the magnitude of the position vector. So to get the magnitude of the position vector, we're going to square all the components of the position vector and then take its square root. So position or the magnitude of the position vector AB is equals to the square root of 9 squared plus 6 squared. So the square root of this is square root of 117, and the square root of 117 is equals to 3 square root of 13. So the magnitude of the position vector AB is equals to 3 square root of 13. So that's how we're going to find the position vector and its magnitude. So now let us proceed to the velocity vector. So a velocity vector represents the rate of change of the position of an object. The magnitude of a velocity vector gives the speed of an object, while the vector direction gives its direction. Velocity vector can be added or subtracted according to principles of vector addition. So the velocity vector, the idea of a velocity vector comes from classical physics by representing the position and motion of a single particle using vectors. The equations for motion are simpler and more intuitive. Suppose the position of a particle at time t is given by the position vector s of t is equals to s1 times t, s2 times t, and s3 times t. Then the velocity vector v of t is the derivative of the position vector. So now, if we're given position vector, so to solve for the velocity vector, we're going to take the derivative. Ato rang kuhaon ang derivative sa position vector para makuha nato ang velocity vector. So now let us have an example. Given the position function r of t, or the position function r of t is equals to 4t I hat plus 7t j hat plus 4t k hat. Find the velocity vector and its corresponding magnitude. So first thing we're going to do is to take the derivative of the position function to get the velocity vector. So here is the given: 4t I hat plus 7t j hat plus 4t k hat. So the derivative of 4t is equals to 4, and then the derivative of 7t is equals to 7, and the derivative of 4t is equals to 4. So our velocity vector v of t is equals to 4 I hat plus 7j hat plus 4k hat. And also we're told to find its corresponding magnitude. So to solve for the magnitude of the velocity vector, like what I've said earlier, that we're going to square all the components and then take its square root. So here, the magnitude of the velocity vector v of t is equals to the square root of 4 squared plus 7 squared plus 4 squared. So the square root of this is the square root of 81, and then the square root of 81 is 9. So that's how we're going to solve for the velocity vector and the magnitude of the velocity vector. So now let us proceed to the acceleration vector. In addition to obtaining the position and velocity vector of an object in motion, we often want to know its acceleration vector at any point in time along its trajectory. This acceleration vector is the instantaneous acceleration, and it can be obtained from the derivative with respect to time of the velocity function. The only difference in 2 or 3 dimensions is that these are now vector quantities. Taking the derivative with respect to time, we find the acceleration vector a of t is equals to the limit of v times t plus the change in time minus v times t over the change in time as t approaches 0 is equals to the dv times t over dt. And the acceleration in terms of component is the acceleration vector a of t is equals to d times v sub z times t over dt I hat plus dv sub y times t over dt j hat plus dv sub z times t over dt k hat. Also, since the velocity is the derivative of the position function, we can write the acceleration in terms of the second derivative of the position function. So the acceleration vector a of t is equals to d squared x times t over dt squared I hat plus d squared y times t over dt squared j hat plus d squared j z plus times 10 over dt squared k hat. So if we're given the position vector, so atong kuhaon ang iyahang second derivative para makuha nato ang acceleration vector. And if hatagan tag velocity vector, atong kuhaon iyang derivative para makuha sad nato ang iyang acceleration vector. So now let us have an example. A particle has a velocity of v of t is equals to 5 t I hat plus t squared j hat minus 2 t cubed k hat meters per second. What is the acceleration function and what is the acceleration vector at t is equals to 2 seconds? Find its magnitude and direction. So solution. So from A, so v of t is equals to 5t I hat plus 2t j hat minus 2t cubed k hat meters per second. So we're going to take its derivative, ang derivative ani para makuha nato ang iyang acceleration vector. So derivative of 5 will give us 5. Derivative of t squared is equals to 2t, and derivative of negative 2t cubed is equals to 6t squared k hat. So our acceleration vector is equals to acceleration vector at is equals to 5 I hat plus 2t j hat minus 6t squared k hat meters per second squared. So to get the acceleration vector at time is equals to 2 seconds, so we're going to substitute the 2 in the time. So we're going to substitute 2 in here in our expression. So substitute 2, so we'll have negative 5 I hat plus 2 times 2 j hat minus 6 times 2 raised to the power of 2 k hat meters per second squared. So atong ipangilisan og 2 ang atoang t kay given man ang atoang t which is 2 seconds. So upon evaluating, we get 5 I hat plus 4 j hat minus 24 k hat meters per second squared. So mao ni ang atong acceleration vector at time is equals to 2 seconds. And now let us get the magnitude of the acceleration vector at t is equals to 2 seconds. So like what I've said again earlier, to take or to find the magnitude, we're going to square all the components and then take its square root. So in here, the magnitude of the acceleration vector at time is equals to 2 seconds is equals to the square root of 5 squared plus 4 squared plus negative 24 squared. And then when solving, we get 24.84 meters per second square. So this is now our magnitude of the acceleration vector if t is equals to 2 seconds. So that's how we're going to solve for the acceleration vector and its magnitude. So that's all for this topic, and now let us proceed to the next topic that is going to be discussed by Gerald Flores. Thank you.
Good day, sir. I'm Gerald Flores from BSCE 2B, and I will discuss to you the derivatives and vector functions. The derivative of vector functions can be understood to be an instantaneous rate of change as well. For example, when the function represents the position of an object at a given point in time, the derivative represents its velocity at the same point in time. To study the calculus of vector functions, we follow a similar path to the one we took in studying real-valued functions. First, we define the derivative, then we examine applications of the derivative, then we move on to defining integrals. However, we will find some interesting new ideas along the way as a result of vector natures of these functions and the properties of space curves. Now, the definition of derivatives and vector functions. The derivative of vector-valued function Rt is r prime of t is equals to limit delta t approaches to 0 r times t plus delta t minus rt delta t. Provided the limits exist. If r prime t exists, then r is differentiable at t. If r prime t exists of all in an open interval ab, then r is differentiable over the interval ab. For the function to be differentiable over the closed interval ab, the following two limits must exist as well. The first is limit delta t approaches to 0 plus a plus delta t plus r and minus r times a times delta t and r prime. The second is limit delta t approaches to 0 minus r times b plus delta t minus r times b delta t. And now this is my example, and here we're gonna find the derivative of given vector. So the given is r times t is equals to cos times pi of t times I plus e raised to the power of t over t squared times j plus 4t cubed times k. First, we're gonna get the derivatives of cos pi t times I. It would be negative pi sine times pi t times I. And for the second part, we're gonna use the quotient rule, so it would be t squared minus et times 2t over t raised to the power of 4 times j. And then we're gonna get the derivative of 4t cubed. It would be 12 plus 12 2 squared times k. And now our final derivative would be t is equals to negative pi sine times pi t times I plus t squared minus et times 2t over t raised to the power 4 times j plus 12 2 squared times k. And next, we're gonna do a simplification, so it would be negative pi sine times pi t times I plus et times t times 2 minus 2 over t over raised to the power 4 times j plus 12t squared times k. So next, we're gonna simplify the second part, so it would be negative sine times nt times I plus et times t minus 2 over t cubed times j plus t squared times k. And now we have our derivative of vectors.
Curvilinear motion, general and rectangular components. The path of motion of a plane can be tracked with radar and its x and y and z coordinates relative to the point on Earth recorded as a function of time. How can we determine the velocity or acceleration of the plane at any constant? Application: a roller coaster car travels down a fixed helipath at a constant speed. How can we determine its position or acceleration at any instant? If you are designing the track, why it is important to be able to predict the acceleration of the car? General curvilinear motion. A particle moving along a curve with path undergoes curvilinear motion. Since the motion is often three-dimensional, vectors are usually used to describe the motion. A particle moves along a curve defined with a path function S. The position of the particle at any instant is designated by the vector r is equals to rt. Both the magnitude and direction of the r may vary with time. If the particle moves a distance as long as the curve during the time interval pi t, the displacement is determined by the vector subtraction pi r is equals to pi minus r minus r. Velocity. What is velocity? Velocity represents the rate of change in the position of a particle. The average velocity of a particle during the time increment pi t is velocity average is equals to pi r divided by average time. The instantaneous velocity is the time derivative of position, or v is equals to dr divided by dt. The velocity vector v is always tangent to the path of motion. The magnitude of v is called the speed. Since the arc length is pi of s approaches the magnitude of pi of r as t is equals to 0. The speed can be obtained by differentiating the path functions. V is equals to ds divided by dt. Acceleration. What is acceleration? Acceleration represents the rate of change in the velocity of a particle. If a particle velocity change from v to v over a time increment to the pi of t, the average acceleration during the increment is the average of a is equals to pi of v and a pi of t minus v minus acceleration of v divided by pi over t. The instantaneous acceleration is the time derivative of a velocity. A is equals to dv divided by dt is equals to d to the power of 2 r divided by dt to the power of 2. A plot of the locus of points defined with the arrowhead of the velocity vector is called hodograph. The acceleration vector is tangent to the hodograph but not in general tangent to the path function. It is often convenient to describe the motion of a particle in terms of its x, y, and z, or rectangular components relative to a fixed frame of reference. The position of the particle can be defined at any constant by the position of vector. R is equals to x, I time plus y, j plus z, x. The x, y, z components may all be functions of time. X is equals to x times t, y minus y times t, and z is equals to y times t. The magnitude of the position vector is r, x squared plus y squared plus z squared to the power of 0.5. The direction of r is defined by the unit of vector. ur is equals to 1 divided by r times r. The velocity vector is the time derivative of the position vector. V is equals to dr divided by dt is equals to d x times I divided by dt plus d times y and j divided by dt plus d times z and k divided by dt. Since the unit vector I, j, and k are constant in magnitude and direction, this equation reduces the v is equals to vx times I plus vy times j plus vz times k, where vx is equals to x is equals to dx divided by dt times vy is equals to y, and y is equals to dy plus divided by dt times vz is equals to z is equals to dz divided by dt. The magnitude of the velocity is v. So vx to the power of 2 plus vy to the power of 2 plus vz to the power of 2 close parenthesis to the power of 0.5. The direction of v is tangent to the path of the motion. The acceleration vector is the time derivative of the velocity vectors, second derivative of the position vector. The magnitude of the acceleration vector is a is equals to square root of ax to the power of 2 plus ay to the power of 2 plus az to the power of 2. The direction of a is usually non-tangent to the path of the particle.